All right, welcome back everyone to session number 5 of Special Relativity and Linear Algebra. Ajeet, we can go ahead and get started.
Great, thanks. All right, so it's been a few weeks. Okay, so as my audience of one already knows, my linear storytelling has been obliterated, but that's okay because there are a couple of ways to tell the story of special relativity, a couple different perspectives to take. And today I want to, I mentioned causal diamonds before. This time I want to tell the story of special relativity entirely about causal diamonds, and I'll be motivated start to finish. It's like you don't even have to didn't even have to come to the first 4 lessons. So all right, let's try to motivate why causal diamonds are the entire game. So just a little reminder, it's maybe I should just start sharing my screen. I'll just share everything. Okay, so if we did a actually maybe I should go to model. All right. Okay. When Mathematica files get too big, doesn't get super happy. It's good to keep these notebooks more under control than this. All right, let's get to Causality Grid. Remind myself what the just spacing. Okay, cool. So Causality Grid, let's do 0.25. Oh, mean space-time environment. Right, of course. That's the whole point. Okay, so a causal diamond would be like one little block here, and we can actually just put that on explicitly with the so space-time environment. This is a this is just like a something I made that's just a little wrapper, so we can put a bunch of stuff in it. So here's space-time environment. It's just a list of objects, and we just stick them all into a graphics. And graphics is very casual. You can put a bunch of things in it just as a list. So I'm going to put a polygon in here, and the polygon is going to have coordinates and or points P. Actually, maybe I shouldn't do it like that. Okay. Yeah. Hold on. All right. I'm actually going to do this from scratch so that we so that this like works the way I want it to. So we have graphics, and let's get some points in here. So all right. So point, we can take a list of points. So we just do P. And we'll do manipulate. So what this is an initial list of those points. So we can do like 0, 0, 0, 1, whatever. So that's a list of points. But then we are specifying the points by locators. And we turn locator auto create to true, which means that you can create new points as part of the interactability. Okay, cool. And then we just need some bounds. So the show will glue 2 plots together or multiple plots together. And I usually have to use a normal just plot to do the outside wrapper, because graphics will automatically adjust what's in it. And that's not how you do that. Great. Okay. And we should probably get some grid lines. So I guess I'll do that in graphics. So in graphics, but we're going to get our grid lines. Oh, actually, can I put, how do I write causality grid? Can I just stick that in here? Causality grid is a dynamic module. I bet I can just put that in there, actually. Wait. No, that's not right. Causality grid is just a list of lines. Perfect. So I can just put that in here. Okay. So, and we're going to add our causality grid. Great. Okay. So if you care about Mathematica, there we go. That's how to do that. But yeah, one of my goals for the end of this is that I actually will give you a working version of all of this code so that you can play with any of this yourself. Okay, cool. So it's causality grid. There's some points, and let me do make this a polygon around these points. And we need more than 2 of them for it to be polygon. Okay, so what are these causal diamonds? So the idea is that this is a causal diamond. Okay. And the idea is that when you hit it with the Lorentz boost, we're going to turn it into a different causal diamond. So these will always be parallelograms, right parallelograms. So these are actually 9 degrees. I guess they're just rotated rectangles. And the idea is that the area stays the same, and all of the weird effects of special relativity are wrapped up in diagrams like this. So, okay, let's tell a story. We have convinced ourselves that space is fake. You can't really say this is all of space. You can't, or relative at the worst, and you can't really say this is how time works for everybody. That's another relative phenomenon. And maybe the most practical way to explain that is in how we even define what a meter and a second are. If you look up the definition of a meter, they used to define it through other things like well, worst case scenario is just like a standard like bar sitting somewhere in Europe. But now they say, oh, it's how far light travels in blah seconds, like 1/1000th of a second or whatever. That's 1/100 billionth of a second or whatever. That's how far light travels in that time. That's what a meter is. But notice that definition is dependent on the definition of a second. And the definition of a second is something that's synced up to like cesium 132 or something like that, just some element, just something that we find sitting around. But the unescapable fact is that our definition of length and our definition of time are linked together. You really only have the relationship between them, the speed of light or speed of causality, that's a constant. And you're kind of free to choose the other one however you want. It's 2 variables we're defining with 1 piece of information. So to drive this point home, I want to make an analogy. So let's say you're in a cave. Okay, you're in a cave. It can be like a 1D like cave. So there's 2 walls and it's dark, so you can't see anything. All right, and you want to know, well, you want to figure out what you can know even. You happen to know, you actually don't even need to know the speed of sound and air. So in this analogy, air is the electromagnetic field and light is sound. Both act by this whole like propagating business where there's a speed associated with how fast information can travel a certain distance. That is the relationship between length and time. So you're in this dark cave. You don't know how far away the walls are. You don't have a ruler. You don't have a clock. So you have no way to reliably measure time, no way to reliably measure distance. All you can do is scream. So you say hello, and then the sound goes, it bounces off the walls, and you hear hello, hello, echoing in your ears. You can't really measure how far apart those were, but you can say which came first. Okay, so you say hello, hello, hello. Okay, cool. The left wall is closer to me. So I walk a little towards the right wall, say hello, and I hear hello, hello. All right, I walk too close to the right wall. I'm now closer to the right wall than the left wall. But that's all I know right now. Okay, this is predicated on the speed of sound and air being a constant. If the speed of sound and air changed over time or over distance or in different parts of the world, then I really couldn't say anything anymore. But this is predicated on knowing that the speed of sound and air is constant everywhere in the cave, at least. All right. So then, I go to Goldilocks zone. I say, hello, hello in stereo. Great. I'm in the center of the cave. Okay. So what I've done is I found the center of the cave. I don't know how far away the walls are, and I don't really know how long my whole little experiment takes. All I know is that I'm in the center. So let's draw that here. So for experiments with light, we use mirrors. Here it's cave walls. So these causality lines you could think of as causality, light, or in our example, sound. And then, right, so here's where you yell hello. And then here, your sound bounces off this wall, or your light bounces off this wall. And here, sound bounces off this wall. And then this event is when you hear both hellos from the walls bounce back to you. So we have 4 events, but only 2 of them you're around for. This event is centered on, this first event is centered on you, and this last event is centered on you. These other 2 events happen over by the cave walls. So you don't really see them happening. You just like know that they do because the sound got back to you. And the whole causal diamond is the experiment. Okay, cool. So right, so when you're in the exact center, these happen at the same time, even though simultaneity is fake. These happen at the same time. And then this is the conclusion of the experiment. Okay. Okay, hello, new attendee. So we're talking about causal diamonds. I'm trying to tell a story of special relativity from start to finish, just with these causal diamonds. So real quick, this is a little experiment. You send off 2 beams of light, they bounce off of 2 mirrors, and they come back to you. So here's the event of starting the experiment, here are the events of bouncing off the mirrors, and here's the event of ending the experiment. The idea is that you can't measure space objectively, and you can't measure time objectively. All we can really measure is them in terms of each other. And if you actually look at how meters and seconds are defined, they're defined in terms of each other, with the only like absolute knowledge being the speed of light. Okay, so I was using an analogy. If you're in a dark cave and there's 2 walls, you can use your echo to find to echolocate yourself into the center of the cave. But you don't know how far away the walls are or how long your experiment takes. You don't have a clock, you don't have a ruler. All you have is that the speed of sound and air is a constant. By analogy, the speed of light is constant. Okay. So, right. So let's make this about light again. Well, it's never about light. It's always about causality, but we can use light. So let's make this about light. Let's say we have 2 people. They're both on Earth, and they have anything that they can compare with each other. They both have like a meter stick, or they both have a rock, the same rock. They both have, 2 identical apples or something like that, or a single photon or a single proton or something. They both have something identical that they can hold, which is a very non-trivial statement, of course. Maybe they have 2 blocks of lead that are similar enough, similar up to some error for our experiment. So both people have 2 blocks of lead. One of them flies off the planet. Okay, we're not talking about the twin paradox. They're not going to come back. This keep going forever. So we want to think about what kind of experiments these 2 different people can do. Okay, so they should be able to do the same kind of experiments because relativity. It shouldn't matter who's moving, because nothing's objectively moving. It's all relative. Both people can say I'm stationary. The person on Earth says, oh, that person flew off of Earth. And the person flying off of Earth says, oh, Earth is flying away from me. Okay, great. So both people, they have their little experiment. They're in some little spaceship. Spaceship's like this little box, very similar to our cave. So this person in their experiment, or person in their little cave spaceship, is trying to do an experiment with light. So they have 2 mirrors, and they have something that emits light and something that's like a photo receiver. Okay, so right, they set up their 2 mirrors, and they have a little pulse of light. It bounces off, and they have a little photo receiver that receives that pulse of light, and they keep adjusting until they get the photo receiver / light emitter centered in their spaceship / cave thing. Okay, so that's their little experiment, with the hopes of creating a little causal diamond. So what have we done? So at that point, they can, if they wanted, define a meter and a second, like a notion of length and a notion of distance. They could say this diagonal here is 1 length unit. We're going to call it a stick, and this is 1 time unit. We're going to call that a tick. I'm stealing this notation from where I learned about causal diamonds, which is a paper that I can't get access to for some reason, but there's an article about it. But anyway, so which is something I'm going to assimilate into these notes. Yeah, okay. There are 2 things that I will definitely have finished next week. 90% chance I've finished next week by the end of the seminar. One is the finished notes, which is 30 something pages right now, but there's some holes and some stuff to finish at the end. I think it's gonna be probably about 50 by the end of it, which is longer than I expected. But there's a lot of I wanted to say about special relativity. The other thing is Observer, which is what I'm calling the special relativity virtual reality thing that I've wanted to make. I'll show you a sneak peek of it at the end. It's very, very underwhelming sneak peek, but the proof of concept that I can make it is there. But anyway, so yeah, I think next week I'm going to have some, at the very least, the barn ladder paradox to show you in virtual reality. So that'll be cool. And I'll make that code open source once it's like working and presentable. So yeah, okay. Right. So what were we talking about? Yes, and I'll put a reference to the sticks or to the causal diamonds stuff in the paper, of course, or in the write-up, of course. So anyway, we're gonna call this a stick and this a tick. So in my spaceship here on Earth, I define this stick and I define this as a tick. Okay, I have a unit of space, I have a unit of time, but I really only have 1 fundamental constant, and that's the speed of light. So keep that in mind. It's 2 units defined with just 1 universal truth. Okay, so it's really just the amount of information there is just it's 1, not 2. Okay. Right. So the person in their spaceship, they perceive themselves as stationary, right? So you never really feel velocity. You can feel acceleration, but you don't really feel velocity. You don't feel yourself, flying around the Milky Way galaxy right now. Well, I guess there's an acceleration component to that you could theoretically calculate, but you don't feel the transverse motion. All right. So you don't feel motion, right? Motion's all relative. So the person in the spaceship considers themselves stationary. They do the same kind of little experiment here. Cool. So both people have a notion of stick. Both people have a notion of tick. All right. We have length units and we have space units. Now I want to show you why there's a perceived difference in these units. So the whole length contraction and time dilation thing. So let's put in a world line of the person on Earth and pretend that they are choose the frame of reference where they are the stationary one. So we'll do a line that goes from just 0, -2 to 0, 2. What happened to my, I destroyed my causal diamond. I can just hard code this actually. So we'll do 0, 0, we'll do -0.5, 0.5, we'll do 0, 1, and we'll do 0.5, 0.5. Great, cool. Now I also have my causal diamond. Let me make that smaller actually. Oh, because my grid spacing is 0.4, which is a weird number to use. Let's make that 0.25, and let's do, oh, and actually that's great. All right, cool. And now I'm going to change some colors. All right, blue for everything. And then we're gonna do green for everything. Cool. And we need a new polygon to manipulate. If you guys ever have questions about what I'm doing in Mathematica, I'm more than happy to talk about that. All right. Yeah, I think this notebook that I give you at the end will actually, oh wait, 3 things. Right. There's also this notebook that I will release a working version of. But anyway, so right, okay. Yeah. Okay, so right now we have this blue world line, which is the person on Earth, and we have this green world line. Oh, because it's in the same place. Yeah. All right, we'll fix that later. It's fine. Okay, so we have this blue world line that is the person on Earth, and we have this green world line, which is our moving observer. I made them move at some velocity less than the speed of light. And let's kill this this polygon real quick. Okay, so the idea is that we want a new causal diamond for this person. Okay, so this moving observer, relatively moving observer. Okay, so how do we even do that? The idea is that the area of the rectangle has to stay the same. Okay, so okay, well, first off, why? Why does the area of the rectangle have to stay the same? This is why I insisted that 2 people bring along a common object. So if you just have 2 reference frames, 2 observers in completely different parts of the universe, they can't see each other or communicate with each other in any way. Yeah, of course, there's going to be this scale, this scale problem where there's no guarantee that one of them isn't just like a giant or something. They have to be able to agree on something. They don't even actually necessarily have to bring an object with them. Maybe just they're twins or something. They are the observer is the object. The point is that there's just any way at all to even compare the 2 situations, which is reasonable because otherwise, what are we even talking about? So they both use their little block of lead to tessellate out a little region. And the block of lead existing is tessellating itself through time. So the idea is that we choose to preserve the area of the causal diamond for the purpose of being able to say anything about anything. And we talked about this 3 weeks ago. I think, if I remember correctly, I made you at least a little satisfied by talking about, like, if you have a block of lead and it's like smeared out through space and time, like you kind of push some of that lead into the future. Where to go? Oh, went into the future. So lead is not preserved. The amount of lead in space is not preserved. I mean, partly just because simultaneity is a silly thing to talk about anyway. And the amount of lead in time is not preserved in a sense. But the two dimensions together, the amount of lead meters seconds is preserved. And there's good reasons why that should exist. Like, conservation of, not conservation of energy, but conservation of like energy time and some argument like that. Okay, so it's a couple different reasons why we would want the areas of these causal diamonds to be the same. Okay, so that's one property, is that the area of these causal diamonds is going to be the same. And then the next thing that we want to do is only draw the sides of the causal diamond along causality lines. And that's because this little experiment that each observer is doing, the only tool they have at their disposal is the speed of light. They can send light rays in the right direction and light rays in the left direction. That's all they've got. We shouldn't define we shouldn't define a little laboratory diamond through space and time using anything other than the speed of light, because that's our only like fundamental that we have to work with. Okay, so the sides of it have to follow the causality lines, and the area has to be the same. So then the question is, what is left free? It's the slope of this line, but that's from the way I started the story, that's not a free thing. It's the velocity at which the person flew away from the planet. So if we assume that we know the velocity that the person flew away from the planet, we now have the problem of drawing this little rectangle where we know what this slope should be. We know that the rectangle, and we know that the area is the same. And that's actually all the information you need to draw the rectangle. And I'll put the full fleshed out calculation in the notes eventually, but by next week, yeah, I'll put those in the notes. The full calculation for how to get the sides of these diamonds. But right now, I wanted to like illustrate what's going on. So let's let's get this slope to be. I want the slope to be 2. I think actually is already slope 2. Yeah. Okay. Good. So let's see, rise over run. So it goes 4 in 2. Yep, slope is 2. Good. So that's this green observer is moving at 0.5 the speed of light. Okay. So let's draw our causal diamond. So you know what? Maybe I should turn the opacity up so that we're going to be able to see both. So let's put opacity at 0.5 or opacity down. Okay, and then let's use, instead of blue, we can use blue, and then here we'll use red. We're already using red. What are 2 primary colors other than red? Blue and yellow. Those are the ones. Yeah, use yellow for this. That's awful. Turn thickness up. Great, that worked. All right, cool. So now we want to draw this other polygon. So polygon Q. And polygon Q, let's see if I can do this without giving myself too much of a headache. So this is going to be 0.25, and that's going to be 1, and that's going to be 1. It's going to be 0.75, and this one should be something which I need to figure out. And I did that wrong. So the left point, instead of negative 0.5, it should be negative 0.25. That should be 0.25. Good. Okay. And then the right point, or the rightmost point, is going to be, instead of at 0.5, 0.5, it's going to be at 1 and 0.75. There we go. And then this thing should be at 0.5, 1. Great. Yes, that is. Wait. Okay. I have an idea of how to make this something built into the model where you can just like choose a velocity and then it'll draw the causal diamonds with it. So that's the dream for the final form of this thing. And that just needs to go to 0.75. No, obviously not. The slope is 2, which means this should be double what that is. So if that's at 0.75, that should be what am I doing wrong here? You know what? Screw it. I am just going to cheat and use locators like I intended at the beginning. Ah, great. That lines up almost. That doesn't line up because the slope of the line does not matter. Or slope line matters, but there we go. Okay. So the idea is that when you do the experiment in the resting frame, this is the start of the experiment right here. This is stuff that's going on in the walls, and this is the end of the experiment. Along this world line for the moving observer, the experiment starts here at the same place, or you could have shifted this whole diamond like up here somewhere, like after they've already flown away from Earth. It doesn't really matter. You can just think I superimposed them both onto the same origin. And their experiment ends, it also has to end along their world line, right? So in fact, I could, actually, I don't want to move that. Okay. Their experiment has to end on their world line also. So where's I going with that? Yeah, okay, cool. So the area has to be the same, and that actually fixes what our sides are. So like this is A, this side length is A, and this side length is 1/A. And then that's, we have all the variables we need to deduce what those should be. Okay, so right, so what happened? Well, this is going to be a tick now for them. So when you measure, so here's the key to why space and time seem to get screwed up in special relativity. It's that space and time are something that have to be measured. Okay, so if an observer is moving relative to you, when they measure time, it's two discrete measurements. It's like a starting point and an end point. So they measure the elapsed time, at the positions that they happen to be in. So here's the first measurement, and here's the second measurement. So time for them is going to be this length along here. This is their tick. This is the tick of their clock. And then conversely, this is the stick. So here, this diagonal line was our stick. This was our little ruler that we would use to make any kind of simultaneity argument, any kind of argument about space. And now this is that stick, this diagonal here. So that's the tick, and that's the stick. So this is where this time dilation and space contraction illusion comes from. So here, this length of time for this tick, I mean, this is like how they define one tick of the clock. But if you just like draw a horizontal line over here to ours, we see that it looks like more time for us elapsed than for them. It's like time slowed down for them. Did time really slow down for them? I mean, what does that even mean, right? Okay. So, and as for space, it's the length contraction. Here we have to use that kind of backward reasoning about their unit of length is bigger. Let me make a note. I owe you a better explanation about why that works one way for one and one for the other. So I'll tie that loose end. Okay. Yeah. Okay. Those are our causal diamonds. Yeah. Let me do something a little less agonizing than my little squares and cheat a little bit, and take you to a pre-made picture. So I have big hopes for these Causal Diamonds images. These are just some images, but I want to fully make a fully interactive version of this in Mathematica, where you can just create any scenario you want. So let me start with the with this stationary observer and moving observer. So all measurement points, so the edges, so the vertices of the causal diamonds have to be along your world line. And that's really the key to where these effects come in, is that when you make these measurements about what space and time even are, that has to be along your world line, because I mean, you're making the measurements. So if we pick a universal units of space-time area, then we see that little area element, the causal diamond, gets stretched out. The area has to stay the same, so it gets compressed in one direction and stretched in the other. Yeah, but then, right, and this comes back to our motivation for how we got the Lorentz transformation. So a refresher on that, I made an argument several weeks ago, actually, about where to get the Lorentz transformation from. And I was saying to avoid any kind of Causal Doppler effect, you're going to compress along causality lines in one direction and expand along causality lines in another direction. So this is that compression and this is that expansion, and they have to cancel out, so that we choose for them to cancel out, so that we can talk about similar little laboratory elements, if you want, or causal diamond elements for both people. The total like space-time area of the laboratory is the same for both observers. That's like kind of a way to motivate why we care about equal area causal diamonds. Okay, cool. All right. So questions so far before I go into how to actually use these things. We're going to talk about the barn ladder paradox, and we'll talk about the twin paradox in this new formulation, and then we will wrap up for today. Okay, cool. So how do we actually use these things? So the space-time interval is actually the same thing as proper time. Okay, what do I mean by that? So in a world where space is relative and time is relative, and our only thing that we can all agree on is the speed of causality, our one like savior is this space-time interval, x squared minus t squared. That's something that always has to be conserved for everyone. So right, so I need to argue why this is the same thing as proper time. Yes, okay, cool. So, right, everyone has their little laboratories and they can do this little experiment and it'll look the same in anyone's reference frame. Okay, so the space-time interval way of saying that is they have the same little laboratory area, and the proper time, so proper time is the time experienced by the observer. Way to say that is an invariant way to talk about things is how many ticks by that observer they've experienced. So for example, if I say in this schematic anyway, Bob experienced Bob at 5 seconds, it's ambiguous what I'm talking about. 5 seconds of my time, 5 seconds of your time. There's no universal time to appeal to. What is 5 seconds? But what is concrete to say is 5 of Bob's seconds. So 5 seconds of proper time for Bob. So 1, 2, 3, 4, and then 5 would send out to here. So this is 5 seconds of proper time for Bob. And that's an invariant thing. I can say 5 seconds, Alex can say 5 proper time seconds for Bob. Bob can say 5 proper time seconds for Bob. And no matter how fast you see the moving observer going, even if you see them going the other direction, you always know what 5 ticks of their clock means. That's invariance. Right, so 5 ticks of my clock. So I should never describe how you're moving by my clock. That's like the moral of the story. But if you always use the clock of the moving observer, it actually doesn't matter how fast the relatively moving observer is going. It's still saying the same thing to say 5 ticks of their clock. It's how many ticks of my clock it is depends on how fast I'm moving relative to you. The 5 ticks of their clock, that's something we can all agree on. It's invariant of observer to say 5 ticks of Bob's clock. Okay. Similarly, we could say 5 causal diamonds of Bob's. Here we see 4 of them. We say 4 causal diamonds of Bob's. So no matter how fast Bob is moving relative to you, we can always measure how many of these causal diamonds he has traversed. How many times Bob was able to do this little experiment is another way of thinking about it. Okay, real quick, I want to mention, I want to address how sometimes it feels like we're talking about a scalar and sometimes we're talking about an area. This is really deep. So, okay, so right, so the space-time interval, yeah, okay, I'm gonna table the space-time interval for a second. We're gonna talk about causal diamonds and proper time, right? So you can specify how many causal diamonds by just how many ticks along the moving observer's clock. Because if you know how many of these diagonal elements you are, the moving observer is moved, you know how many causal diamonds exist, aka how many times they've done the experiment. Similarly, if you say, oh, Bob has done his little echo experiment 5 times in his little spaceship chamber, then we know that that's 5 ticks by his measurements. It's the same thing. So, but why? Why in special relativity through linear algebra should an area thing be linked to a scalar quantity? The proper time, or space-time interval, is a scalar number, but these little causal diamonds is an area argument. So we went from scalars to area. Right. Okay. So this is kind of what motivated me to do the entire seminar, was a deep connection between dimension 2 and dimension 0. So what's the idea? When you have a vector space and you define a metric on it, the metric is an object that takes in 2 vectors and spits out a scalar. It's if you like differential geometry, there's this Hodge dual isomorphism between the second exterior product of the cotangent space and the like the 0th exterior product, like just like the space of scalar functions. So right, you have a vector space, which is a 1 vector type of object. You have a metric, which is a 2 vector, like a O2 tensor kind of object, and you have scalars, which are 0, tensors. But the idea is that you have a whole bunch of length transformations on the vector space that you can do to see the space differently. It's these time and space and stuff aren't invariant under these Lorentz transformations. But if you go up into 2 dimensions where you have a metric, everyone agrees on the space-time metric. Everyone agrees on the space, or aka the space-time interval. Everyone agrees on how to measure this. Everyone agrees that there is this invariant kind of distance. But also you could go down and use this scalar property and say, oh, everyone agrees on how many space-time experiments they're able to do. That's kind of an abstract way of explaining it. The idea is that I want to take the physical mysticism out of this by explaining it's just a linear algebra problem. So you have a vector space where things happen. It's a 4-dimensional vector space, or for us, it's a 2-dimensional vector space. One of those dimensions we like to call space, and one we like to call time. But what that even means is very hard, or is meaningless to pin down. It's arbitrary rather to pin down which one's space and which one is time. But what's not arbitrary are these eigenvectors, because the speed of light is constant. Okay, that's where we get the causality grid, which is this background grid. And after we have a background grid, we have 2 ways of approaching the idea of being able to agree on something. One is to go up a dimension, and we use a space-time interval. We use a metric. Right, we use a metric. It takes in 2 vectors and spits out a number. The other way to use that number, which is counting ticks by a local clock. Okay, so this is the key. It sucks, but the reality of it is that back when we started physics, we defined space because we looked around and said, oh look, all this space here, it's staying still. That seems like a thing that exists, and we felt ourselves we saw ourselves aging, right, and the sun going around and this tick tick ticks of clocks and stuff. Like, oh, time is a thing, right? So we have a dimension of space and a dimension of time. Okay, sort of. Those are things that we can salvage from special relativity if we try really, really hard. But it turns out that this 2, or rather 4-dimensional world we live in, space and time are awful ways to describe it. They're not invariant under different reference frames for observers moving at different relative velocities. But if you go up or down a dimension, there are things that we can salvage. You can, if you go up a dimension, you get the space, or not a dimension, sorry. I never know what an order, I guess. I guess you know what I mean. When you go from the cotangent bundle to the second exterior product of the cotangent bundle, it's not a dimension up. I'm just gonna call it an order, whatever. So if you go up an order, you get a metric, which is an O2 tensor, right? It's still 4 vectors, or like, you know, space-time vectors in 4 dimensions. There's still 4 vectors, but there's 2 4 vectors. An O2 tensor over a 4-dimensional vector space is like 2 4 covectors. Gross. Okay. Anyway, you go up and get a metric, or you can go down and get a number. And those things are actually the same thing. The idea of a metric is a little machine that takes in 2 vectors, lets you compare them to give you a number. And if you can do that over all the pairs of vectors, you now have a scalar function that you can use for things. Okay, so right, so there are 2 ways of thinking about this. Ticks along the clock of a moving observer, so that's proper time, or causal diamonds, which is like an area argument. And those are the same thing through the lens of linear algebra, because a metric is a thing that takes in 2 vectors, like 1, 2, and spits out a number. Great. Okay. Right. So let's all. Okay. Questions before we solve some paradoxes. Cool. Okay. Let's do the barn ladder paradox again. So the barn ladder paradox. Let's say the farmer is sitting on top of the barn. Okay. And the sun is running with a ladder through the barn at relative physics speeds. And the farmer, who's at rest in his own reference frame, when he sees the sun inside the barn, he's going to close the doors he's sitting on top of the barn in the center of it. He's going to send a signal, like a light signal, to both ends of the barn, which will trigger the doors of the barn to close. And then, you know, that signal he sees the doors close, and the light from the closing doors comes back to his eye. It makes a little causal diamond. Let's say the red is the farmer. So bam, here. So let's say I don't know, here is where he observes the ladder fitting inside the barn. So he says, oh, okay, now's my cue. So he sends out these 2 light signals. Here the right door closes, and here the left door closes. From his reference frame, these are simultaneously happening. The left and right door is closing. And then he gets receipts. He says, cool. At the same time, I see the left one close and I see the right one close. Great. So from his perspective, he trapped the ladder inside the barn for a split second, and he saw it happen, and the doors closed at the same time. But as we talked about the punchline before, for the barn ladder paradox, simultaneity is not preserved in different reference frames. And here's why. So let's say the sun considers himself stationary, and this is the farmer now. This is the barn and the farmer. The barn and the farmer are moving. So this line gets Lorentz boosted into this line, and we see into this line plus a little bit up here. So it has to be 5 ticks, but we're not worried about the end of it. We're looking at this part of it. So third block to third block. We see that the starting point where he sends off the 2 light rays, that's fine. But this event now, the left door closing, happens before the right door closes. And then the farmer gets the 2 receipts here. But what's so tricky here is when the farmer gets the 2 receipts here, the moving farmer, so we are now the stationary sun, and the farmer and the barn are moving. The farmer, we see why the farmer still thinks that these 2 events happen simultaneously, because he gets the light rays from both of them at the same time. They both intersect right here. When light gets to your eye, you don't have a way of knowing how long it got to you. In astrophysics, we do, because the universe is expanding. So when light gets to you, it gets redshifted, it gets stretched out. So if you know how bright a galaxy should be, if you know what the spectral lines coming from a galaxy should be, which we do because we know what elements are in that galaxy, but that's because of a whole bunch of other science. It's not anything like my idealized little scenarios with caves I've been setting up. There's a whole bunch of information that goes into it. And I guess really there's assumptions. There's always a chance that the distant galaxies are made of super strange things or something. But we have to assume that, you know, our physics here on Earth has some bearing on distant galaxies. So anyway, we assume we know what kind of elements are supposed to come out of distant galaxies. So we know what spectral lines to observe, like what frequencies of light to come. We get slightly different frequencies of light. They're redshifted because they got stretched out, as the universe got stretched out between us and the galaxy. And then how much it got stretched out, we reverse engineer, because we know how fast the universe is expanding, to figure out how far away the galaxies are. That's like a whole bunch of science going into figuring out how far away the light came from, a whole bunch of science. Just a priori, if you're sitting in space and light comes to you, you have no idea how far away it came from. If you have a field of vision, you can see like, things are smaller or bigger in the sky, but to know if they're shrunken down or not, you still have to know what the object is. Back in ancient days, they saw the sun and the moon in the sky, and they appear the same size in the sky. Like how insanely shocked would they be to learn that one is 30 Earths away and the other is 93 million miles away, right? Like one just happened, one is insanely farther away and it just happens to be that massive. But just by looking at it, you can't tell which is how far away either are. You don't know anything about the absolute size or the absolute distance away. You just see how big they are in the sky. So the same principle here. When the farmer gets this beam of light and this beam of light, he's like, oh, cool. The doors closed at the same time and I got the light from both at the same time because I know how long the barn is and I'm sitting in the center of it. But the stationary observer would say, oh, the farmer's so deluded. He's this thing clearly happened later. It's just the light got to him at the same time. Turns out the stationary observer is deluded also. It's all relative. But all right, cool. So that's why we can disagree on these things in the different reference frames, because simultaneity is not preserved. Okay, cool. So that is the barn ladder paradox with causal diamonds. Okay. Right. So yeah, questions on that, or do we like that? No questions would be great. I think it works. Okay, cool. So for a little cave example, if you were in your spaceship flying away and I'm in my spaceship stationary on Earth, when I see you doing your little experiment, you're like, so imagine the spaceships are caves now. I'm just going to take the analogy to sound because I like that one. So you're in your little spaceship cave flying away, and I'm in my spaceship cave on Earth. When I see you yelling in your spaceship cave, like from Earth, I'm looking at you flying away from your moving cave yelling, right? You found the center of the cave, so to speak, right? You found the center of the cave, you think, and you're like yelling, you're like, hello, hello, in stereo, right? Well, I'm sitting here on Earth being like, he's not in the center of the cave, he's like to the left of it. Then he yells, but since the whole cave is moving that direction, and then here's where the analogy breaks down, I guess, because this air molecules would move with your system. Turns out light molecules don't move with your system. When he yells or he sends off his little light pulses, it hits the left wall first. It's just that the whole spaceship's moving this direction. So then he catches up with the other light ray, and then his little experiment's silly. He's not in the center of it, and he's not in the center of his experiments. The whole thing is skewed. The whole thing is stretched out like this. The thing is, you would never know. So and more than that you would never know is that it's all relative. So this is the crux of all the special relativity paradoxes, is that there's only one piece of data. We say things about space and time, but you only have one piece of data, one constant, and that's that the speed of light is this ratio between space and time that is constant everywhere. So anytime almost every special relativity paradox is something like this. Oh, well, something weird happens in space relative to time, or something weird happens in time relative to space. But it's always predicated on the idea that we can both agree on some notion of space and time. We can never do that. That's two pieces of information. You and I can only ever agree on one piece of information, and that's the speed of light. So, right. So it always tries to get more out of you. Like, oh, well, the ladder does fit into the barn. No, that's you can't have a statement about space and time. The ladder fitting into the barn is saying that both ends of the ladder in space are in the barn at the same point in time. It's a statement about space and time, and it's just too much information, and you can never get that much. And there's always one degree of relative, one degree of freedom from relativity. Okay, and that degree of freedom is it's weird because the one that we know is diagonal to our notions of space and time. But maybe that's kind of beautiful though. We have one piece of information and two dimensions, and it's actually diagonal, where the solid one is. The other degree of freedom, I guess, is also diagonal in a sense. Maybe we're getting too abstract now. Okay, one more thing for today. Do a twin paradox. Wow, actually, I might end at 7 this time. So here's the twin paradox. So I kind of hate the twin paradox because the way that's formulated is there's this instantaneous acceleration. The twin that flies away from Earth instantaneously changes directions and comes back. But what's really crazy about it is that it doesn't break any physics to instantaneously accelerate. If this is a smooth curve here, it doesn't change it at all. But just for my sanity, I'm going to say this is not instantaneous acceleration when the twin that stays on Earth, twin that leaves Earth. Question is, who ages more? So the twin that leaves Earth, I'm going to say when they get to like Andromeda or something, they have an insanely powerful rocket booster, and in some finite amount of time, they change directions back to the same speed in the other direction. So opposite velocity. So maybe they experience like 10 million Gs or something when they do that acceleration. But I'm imagining some little smooth curve here. Well, sorry, not analytically smooth, like in a mathematician sense. Second derivative exists and is continuous. Sorry, this quick tangent. This is something that I constantly bang my head against the wall with being a mathematician pretending to be a physicist is 10 million G's just like in the Kerbal Space Program. Nice. Yeah. Yeah, so I'm constantly trying to think like, what is the path that an object follows? So physicists say, or Newton likes to say, right, it's always the net force on it that causes the acceleration. Okay, so the velocity is always going to be continuous because it's sourced from this acceleration function, which is the next derivative. But where does the acceleration function come from? That comes from the combination of a bunch of forces. Where do forces come from? Well, forces can kind of turn on or off. If you jump off of something and land on the earth, like you're standing on top of your car and then you jump off your car and land on the ground, the normal force of the earth doesn't kick in until you hit the ground, and the gravity force switches off when you hit the ground, or however you want to think of them, canceling out, whatever. Just pick one, right? But then it's a discontinuity, right? But is it really a discontinuity? Because you gradually land onto the earth. If you zoom in on your shoes hitting the earth, all the electrons will like compress, right? So then the force of the normal force of the earth, or the force of gravity, gradually switches on and off. Like I have this question, like as a mathematician, like I'm always like wondering how smooth should the motion of anything be? Part of me wants to think that all curves, all the motion of any object should be infinitely differentiable. It should be totally smooth, because if it's not, like if it's not smooth on like the seventh derivative or something, that means that there's some physical reason why something switches off discontinuously. And I can't think of anything that turns on and off discontinuously. I feel like everything in the physical universe should be smooth. But maybe not. Maybe for Newtonian physics to make sense, you only need that it's a continuously differentiable function, and acceleration is allowed to be some weird discontinuous function because forces switch on and off. I don't know. It's actually an unanswered question in physics, whether forces switch on and off instantaneously. Like if you see fundamentally, energy is transferred between atoms by electrons switching energy levels. The question of how long it takes that electron to switch energy levels is an open question. There are people that think that it happens literally instantaneously, and there are people that have tried to catch it in the middle of jumping between energy level, and they think they have. So we're not actually sure. And I run into this kind of problem all the time when I'm thinking about this. Do I think like a mathematician and think it's smooth, or do I think like a physicist and say, whatever, it's differentiable and it doesn't impose no conditions past that? I don't know what the right answer is, but okay. So anyway, this is smooth by any definition you want, but actually doesn't have to be. So the answer in this physical scenario is that it's piecewise differentiable. Doesn't have to have the second derivative be continuous, and anything after that doesn't even matter. So, okay, it's a mirror if you want, apparently. So anyway, that's just a sign that this part of it is not really important. This part of it is not important, apparently. Okay. So, all right, let's talk about this. So here's the observer that's staying on Earth, and here's the observer that switches directions. So the idea is that so the paradox is that both people are doing the same thing. Both twins can always say the other person is moving and I'm stationary. So why should one age more than the other? But the thing is that one changes directions. So the actual period of acceleration can be arbitrarily small. But the idea is that Bob, or the other twin, the twin that left Earth, is always like accruing distance away from Earth, and then somehow they end up back at Earth. Well, it's because they change directions at some point. And the way to see that with causal diamonds, that this person is the one that's that's getting time dilated in a non-relative way, is by counting the causal diamonds or the proper time. So here we see the person on Earth can do 5 experiments. And here we see the person that's moving away from Earth can do 4 experiments. 1, 2, 3, or sorry, 8. Sorry, this is 10 experiments. This is 8. I can't count. Okay, so 10 experiments and 1, 2, 3, 4, 5, 6, 7, 8 experiments. And this is just super freaky because the acceleration can happen for an arbitrarily small amount of time. But the idea is that this person is doing something relativistically interesting, and that's that they're changing directions. That's an acceleration. They're doing something that's not just throw your hands up, it's all relative. They're the ones that are doing something special. And then they end up being the ones that age slower. They're the ones that they are the ones that is having this skewed, slower experiment. Their experiments are slower. They come back on Earth, and A and B are like, oh yeah, I did 10 experiments, and B is like, oh, I only did 8 experiments. I thought I was doing everything normally. And A is like, ah, okay, sure you did. We all know that you accelerated. You turned around over there. There's actually another paradox where what if we lived in a closed loop universe where this end is glued to this end, like topologically? So it's like the universe is topologically a cylinder in this direction, so that this person could just like jump off the right end here and appear over here and intersect here. And then the question is like, oh, well then why? So in that case, there is no acceleration. So why is B aging slower? So before I answer that second paradox, do you understand the answer to this paradox and the new system I'm setting up?
So I have a question.
Okay, cool.
So in the previous paradox, you said if we switch perspectives, we can simply switch, the meaning of the pink and the blue.
Yep.
Right. In this case, if you were to switch to Bob's perspective, would you need a separate graph for Bob's perspective on the way out versus one for the way back?
Yes, fantastic catch. In mathematician speak, different charts. So we have this, I mentioned this, I think last session, we have this constant issue where we're in these kind of space-time diagrams, we're conflating the tangent space with actual space. Like we're using like a local trivialization of the tangent bundle if you want, or whatever. Because when we talk about these slanted things, it's always a statement about velocity, but this is space-time. So, right, so to switch their positions here, you need to break it into 2 segments. Below this line, you can totally just switch the meanings. And above this line, you can totally just switch the meanings. But there's no good way to glue these 2 diagrams together. I would like to say a note on this in my final write-up about salvaging space-time diagrams for arbitrary motion. But just like the problem is that, okay, so the problem is that, so if you can imagine okay, so you see this is the velocity line here. So this is time for B. Space for B, which we've already bashed on a lot, is going to be, so this angle here, if you take that same angle here, there's a line here for space, okay? So that's the new simultaneity line for Bob. So his simultaneity lines are gonna be going like this, like bam, 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 bam. But at this point, they switch to going like this. And that means that past here, the simultaneity lines are crossing. So his future and his past get mixed up. It's just another argument about the simultaneity lines are a dumb thing to say anyway. But what I'm trying to get at is that if you try to take these diagrams too seriously for anything other than linear motion, you run into local trivialization issues. And those are things that I don't want to talk about because I don't know if these diagrams can even accurately handle that kind of thing. I think these diagrams really work when you're being naive about it and say, oh yeah, well, right, because like if you're moving in a constant velocity the whole time, then yeah, then the total delta in x and delta in t is reflected by these like Lorentz boosts and stuff. But the Lorentz boosts are statements about the infinitesimal. So you can only extrapolate the infinitesimal to the global if it's a constant motion. It's like saying I drove down the highway at 60 miles per hour for an hour. Like, did you really? I mean, like, your total delta x was 60 miles and your total delta t was an hour, but you totally could have fluctuated along the way. It's a very different statement to say a global delta x versus delta t versus an infinitesimal velocity. But the statements in special relativity are always about the infinitesimal, but the diagrams that are worth anything are always about the global. So the only way to draw things that make that offer any insights are to use constant velocities. And here we totally screw that up by changing directions. So here you can't really switch to the perspectives, which is good. That's the whole point of the twin paradox, right? Is that they experience different things. So great question. That's right at the heart of the twin paradox. Okay, Petra's question. What's up?
This might be kind of trivial, and if it is, just let me know. But I mean, so when I let's say I shine my flashlight at a mirror and I'm like trying to measure how long it takes for the light to get back to me, the light that has passed, or the time that has passed for the light that I shine at the mirror, would be different than the light that, or the time that I've experienced. Correct?
Sorry. So you're doing the experiment and you're measuring the time?
Well, I guess it doesn't. I mean, I could have like a photoreceptor type thing to measure time. But my question is more just like, if I do this experiment where I like the experiment that you described, where like you're measuring time by like letting light go out and then like measuring how long it takes to get back. The time that has passed for the light that goes out should be different than the time that has passed for you, because it's moving out and then slowing down and coming back. And so like this, like you're showing here, like, because in essence, what Bob is doing is the exact experiment that you're doing with light. It's just Bob is not the light.
Great, good, fantastic. That was the whole point. This lecture got into your guys' heads. Fantastic. Yeah, that's the entire point. So the whole point is that anytime anyone talks about space and time, they have to do little experiments to even talk about space and time. Like, I defy you to give me a definition of time or space or a second or a meter that doesn't come back to the speed of light. It's impossible to define space and time, as far as modern physics understands. It's impossible. Maybe, an awesome dream would be somehow to salvage these things. But anyway, but it's impossible to define notions of space and time in any way other than leaning on each other, because the only thing you actually know is the speed of light. So if someone's going to measure time in their spaceship or stationary on Earth or whatever, they have to do these little experiments. You can't really measure the time it takes for light to go to the mirror and back, because what are you using to do that measurement? You're using some mechanical little clock, and the gears in that clock are made of atoms, and the atoms in that clock hit each other by sending electrons between their energy levels, and that is both, to move the electrons between their energy levels. And the mediating force of the electrons moving between the energy levels are little photons. So you just come back to photons moving again. Using like a physical clock or any kind of clock to measure the time it takes for the light to bounce off the mirrors is totally begging the question, because you just brought the question back down to photons bouncing around again, except now it's photons inside your little stopwatch instead of photons in in your macroscopic like experiment. It always just comes down to, you have a speed of causality that things unfold at, and there's no objective way to measure that. So if you're sitting here and you send light rays at your two mirrors and they come back, you can't say, oh, it took 1 second, any unit of time for that to happen, and you can't say, oh, those are a certain distance away, without referring back to the speed of light. All you can say is that I did this experiment n times, and that defines a relationship, a ratio between the time the experiment took and the length of the experiment. It defines a ratio between those, but that ratio is just the speed of light. And that's the only piece of information. You can't objectively measure the time, and you can't objectively measure the distance. All you can do is count the number of experiments you do, or the number of ticks along your clock, or your proper time, or your space-time interval, or your area elements, all the same thing. Did that answer your question?
Yeah, that's kind of what I was. That's what I was asking.
Fantastic. Yes, great question. That's the kind of question I need to put these thoughts into the right words. Awesome. Okay. So last thing before I let you guys go. So there's this other special relativity paradox. What if we live in a closed universe? So what happens if I fly off a bunch of light years that direction? I end up back here. It's possible. We haven't ruled that out. What's past the observable universe? We don't know. Maybe our universe isn't just like an R3 or an R4 of the vector space. Maybe it's closed. Maybe we live in a donut or a cylinder or something. Maybe it's something that's really weirdly curved, actually. But if there's wormholes, then there's certainly a non-trivial topology. Like there's definitely loops. If there's wormholes, there's definitely points where space like pins back together. But the question is, what if there's even one loop anywhere? What if it's a cylinder? So one dimension of space and one of time. What do we live on? A cylinder in space and linear in time. That'd be really weird if it's a loop in time, but who knows? Anyway, so cylinder in space. So cylinder. So space is a circle, S1, and time is R1. So maybe the universe isn't R cross R. Maybe it's S1 cross R. Okay. So then when we get to here, you teleport over to here. You're not teleporting. It's just space is glued, and then over to here, and then Bob just continues his travels. In that picture, it doesn't look like in that picture, he never changes directions. It just washes away this whole little point here. But the idea is that he's accelerating in some like abstract way. There's like this radial component as he runs around the cylinder. I think I owe you a better explanation than that. But the what I'm trying to get across here is that this little negligible acceleration that I spent a tangent explaining why I have a problem with, you can do away with it entirely, and you can live in a closed universe, like a cylinder universe. And the paradox is still resolved by saying that this person who flew away from Earth and ended up back at Earth is actually doing something relativistically interesting and not completely relative. So in a closed universe, they fly away from Earth, and then they end up back at Earth. Man,
I object.
you object?
Because if we imagine that space is toroidal, and you wrap around somehow, and I don't know, I have trouble saying that that's an acceleration, because you're moving simply through the dimension as it exists.
Right. So on these space-time diagrams, in this now that we have a cylinder, we do have a constant velocity, so that it salvages some of our local versus global issue. But now the issue is that our entire shape is no longer a plane; it's a cylinder or a torus or whatever. So now we can use our whole switching arguments again, but we can't use that the whole thing is a plane. So where's that going to bite us? So let's say you have a cylinder universe, circle in space, and then R in time. The Alice observer is just a vertical line up and down the cylinder, like a seam in the cylinder. But the Bob observer, he does a helix around here and makes a loop. So the idea now is that you can't switch these, because even though the paths are both just lines, they're the way they're drawn on the global surface, right, is topologically different. One is a closed loop, and okay, if you project down, one is a closed loop and the other is not. So geez, that's not I don't know if it's any worse of an argument than anything I've said so far, but but they're topologically different now. So there's never a topological difference between anything you do in a flat spacetime. In a simply connected spacetime, there's never anything topologically interesting. There's no closed loops even. There's never even closed loops really, because you can't really get back to where you started, because you have to go backwards in time. That's actually how Stephen Hawking formulates the whole idea of time travel, is really you just want any kind of closed loop. But anyway, so the right, but if you have a topologically interesting space-time, you can have topologically different curves, right? And actually, I can make this a little better for mathematician speak. We are using linear transformations on the surface, or more generally, we're just doing homeomorphisms, self-homeomorphisms of the isomorphisms, right? No, wait, whatever, it's fine. Self-homeomorphisms of the surface to land it back on itself while preserving certain properties, actually really just preserving the speed of light. That's really all that we're preserving. You take a homeomorphism of the space back onto itself. That's what these Lorentz transformations are. It starts with the space and it lands back on space-time. It starts with space-time and lands back on space-time. But this mathematical space back to itself, but things get moved around. There's no homeomorphism of the cylinder that you can do that will take that helix to a line without violating property X. There's definitely some good property about a cylindrical universe that you'd have to destroy if you can just relativistically take lines to helixes. Do we buy that? That sound all right?
Well,
you have to twist all the
sounds
space.
a little better, but fundamentally, it seems to be that the argument is based on the notion that that relativity should hold in the projection onto the Euclidean space rather than within the curved space itself, which I don't see why
you
would imagine that.
Yeah. I wonder if we go to the covering space, if that helps. No, that covering space does not make this better. No. Yeah, so let's see. So if so what would really be the problem? So let's say you have Bob here, and then you have some other C observer that in this amount of time, by Alice's perspective, goes around twice, and something goes around 3 times and 4 times and 5 times. It's like tons of different spirals. If all of those were really the same perspective, that means there's always a reference frame you can take where you're allowed to just twist all of space-time around the cylinder. But then you can do it by different winding numbers. So then there's got to be an issue in there somewhere. Oh man, there's got to be an issue in there somewhere. I don't think it depends on the projection because simultaneity is fake anyway. There's tons of issues with you're right about that. The projection was a dumb thing for me to say. That's not the issue. Yeah. Well, there's definitely things written about this. Probably actually some of the stuff written about this doesn't go up to the discerning rigor that we are now trained to ask about this. But I'm sure there's something out there in the interwebs that will satisfy the level of discussion we've gotten to at this point. But I'll get back to you on that also. Make a note. More convincing argument to why the cylinder thing is a problem. Yeah, I really like the cylinder consideration though, because it does away with this instantaneous acceleration business. Because the instantaneous acceleration here is actually a good thing because it drives home the point that it doesn't matter how fast or how fast they were accelerating, the magnitude of their acceleration or how long they were doing that acceleration. It matters about something. There's something else about changing direction that's fundamentally interesting. I'm sure that'll become more clear too once we resolve the cylinder thing. Okay, cool. So great. Okay, so this was this lesson is very cathartic for me because I feel like I finally got to marry second exterior power of cotangent bundle / quadratic forms / metrics to scalars / proper time / numbers / a single invariant quantity. There's 2, there's 0, and those are the same thing, and they are the way that we can actually reason about 1, which is vectors and space-time and vector spaces and causality grids and stuff like that. So here's where the thing that matters is, and they're actually the same thing, and they help us reason about the thing in the middle, which unfortunately is where the definition of the space and time lay. Great. Okay. So yeah, so that's kind of the punchline I wanted to the entire time, and I think I pretty much said it in the way I wanted to. Just to write it down at some point. But yeah, next time is for tying up closed ends, a couple more paradoxes. Oh, I should probably tell you about relativistic momentum and stuff, which is a fun story. I've talked about energy and momentum and stuff a little bit already, and how like the whole notion of mass and energy flow into each other as you approach the speed of light. Like you have to make clocks out of something. You have to be going less than the speed of light for a clock to even exist. You can't make these causal diamonds. You can't do an experiment that defines a causal diamond without something that's moving less than the speed of light. So then as you approach the speed of light, everything falls apart, and this idea of mass just falls apart into energy. And we can make that concreter with the relativistic equivalent of velocity called form momentum. Okay, and energy and momentum get married with this for velocity or for momentum. So I want to talk about that, but also, and I have a couple of loose ends to tie up, and then most importantly, I want to show you special relativistic virtual reality, and hand you finished versions of this Mathematica notebook and the notes that I have not updated on my website in like months. Yeah, cool. So end scene for today, and thanks for sticking with me this long. It's great.
Well, thanks a bunch, Ajeet. Another interesting session. And so our next session is going to be on Thursday, April 22nd, 6 p.m. again. And that will be the final session, so make sure you're here. See you guys all next week then. Thanks.
Cool. See you next week.
Thanks. Have a good night.